All right, so rejoining part 2 here. We're still on reflections. I'm going to give you another example. F of x equal to 4x minus 9. I'm going to reflect over the x-axis and the y-axis for g of x. So let's do, and again, you guys can follow along here. So I'm going to take f of g of x equal to negative f of x. So I'm reflecting over the x-axis. So I take the entire equation, and I'm going to make the entire equation a negative value, so negative in parentheses 4x minus 9. That leaves me with negative 4x plus 9. I've graphed the two here. My original equation in green here, and then the reflected function over the x-axis, which is the line of reflection, g of x equal to negative 4x plus 9. And by the way, I know I go through these pretty quickly. They're all set up. I assume that as time goes on, you'll learn to pause if things go too quickly. But I tend to keep it quick just to make sure that for those people who don't need for me to take it slow, that you can just go through these videos at this normal pace. And then for those of you who need to slow things down, you can either slow down the pace of the video or you can pause at any time. All right, but I like to keep these going and get to the point. All right, so next for B, we're going to reflect over the y-axis here. So now I'm making h of x, which is f of negative x here. So again, when I reflect over the y-axis, I'm just changing the sign of the terms that have x. So it becomes negative 4x minus 9 here, and I've graphed the two. My original function, 4x plus 9, and then my reflected function over the y-axis, negative 4x minus 9. Okay, so this brings us to our second round of classwork. Again, this work I need to see from you, submitted in some form that I will indicate to you, and I'll keep reminding you of this until we get on to the next couple of videos. And I will specify outside of the video where I want this work submitted. So the next problem is labeled 1.2.2 here, and I'm going to give you the two questions similar to what we just did. So you're going to take f of x is 3x minus 2. You're going to reflect the function g across the x-axis and graph g. Please also graph f of x. You're going to reflect the function h in these two separate graphs across the y-axis, and then graph h as well. So two separate graphs, two separate functions. Please also graph the function f of x on the same graph, and that's what you're going to submit to me. Okay, I'm going to pause here for a moment, and then I am going to move on. Okay, so lastly, we want to talk about stretches and shrinks of functions. And I write the asterisk because I deviate a little bit from the way the book outlines stretches and shrinks. I try to incorporate stretches and shrinks in terms of the y-axis only, just to make things easier. In terms of descriptions, it might not be as accurate as the book, but it's easier to remember, in my opinion. Gets the point across. So I just qualify this as my change, not necessarily a math-oriented change, and also might be different in other classes, but it's just easier, in my opinion, to remember stretches and shrinks this way. So I'm going to give you my version with that asterisk. Okay, so let's talk about horizontal and vertical stretches. All right, so we're going to talk about vertical stretches now. Vertical stretches are going to be that a value, right? So we talked about the slope now in the linear equation representing the stretch, in this case the vertical stretch or shrink. And we're going to say the stretch or shrink is by a factor of the absolute value of a. So that's what those brackets are, and you've seen those before. And when the absolute value of a is greater than 1, so for example 2 times f of x, then we're stretching the line towards the y-axis, meaning the slope of the line is becoming more steep relative to the parent function, which is y is equal to x, where that slope is just 1. All right, so greater than 1, moving towards the y-axis, less than 1, it's shrinking away from the y-axis. Right? Stretching towards, shrinking away. If it's a fraction, a value between 0 and 1 for that value of a. And then we're going to say that it stretches or shrinks by a factor of the absolute value of a. So we wouldn't say it stretches or shrinks by a negative value at any time. All right, at least with respect to these linear equations. Okay. All right, so here's an example. I have y is equal to f of x, and I'm going to shrink away from the y-axis by a factor of 1/2. You can see the slope now changes for the function that's shrunk. All right, so, and then we can do this with transform functions that are transformed or translated vertically, horizontally. In this case, I have a vertically translated function x plus 2. Oh, excuse me. And then I am going to take half of f of x plus 2, and that ends up being 1/2 x plus 1. So I'm taking half of the entire function. Just like with the reflection, when that negative sign is outside of the function, I'm taking half of the entire, taking the negative sign of the entire function. When it's inside of the parentheses, it just relates to x. All right, so in this case, that half relates to the entire function, half of x plus half of 2, which is equal to 1. And so I'm shrinking now away from the y-axis. So again, I'm speaking with respect to the y-axis. Right, so now I'm vertically stretching. Now my slope becomes steeper. 2 times f of x, where a is greater than 1. And you can see I have a transformed function again, x plus 2. Now I'm going to make that steeper by a factor of 2. So it becomes 2 times f of x, or 2 times x plus 2. 2 times x plus 2 is 2x plus 4. And there is the transform function vertically stretched by 2x. All right, so difference between half of x and 2x. All right, so I'm multiplying the entire equation by 2, in this case on the right, and then by 1/2 on the case on the left. All right, so I'm going to give you an example of the vertical stretch or shrink. F of x is equal to 2x plus 2. I'm going to write and graph a function g that is a vertical stretch by a factor of 3. And I'm going to write and graph a function h that is a vertical shrink by a factor of 1/2. Okay, so I'm going to take the first one, 2x plus 2, so it's a factor of 3, so a becomes 3 times f of x. 3 times 2x plus 2 becomes 6x plus 6. I am stretching towards the y-axis by a factor of 3. You can see the original function in f of x as 2x plus 2, then 6x plus 3 as the steeper function here. You see that the y-intercept also changes here in this case. Okay, I'm going to move on to the next one. I'm going to write and graph a function h that is a horizontal shrink. Well, this should be a vertical shrink, excuse me. So I need to change this. This is a vertical shrink. We will talk about horizontal shrinks in just a moment. So sorry about that. By a factor of 1/2, 1/2 of f of x. 1/2 2x plus 2 is x plus 1. So I have my original function. Y is equal to 2x plus 2 here in red. And then the shrink is 1/2 of that function. So I have a vertical shrink. I'm shrinking towards the x-axis, shrinking away from the y-axis. Okay, so this brings us to a third set of classwork, 1.2.3. You're going to do another set of vertical shrink problems here, 2x minus 4. Vertically stretch it by a factor of 3, and then vertically shrink it by a factor of 1/2. So I'm going to give you a moment to copy this down. You can also pause. Okay, let's talk about horizontal stretches and shrinks now. Horizontal now, the a value is going to be inside of those parentheses. Okay, so now we're going to talk about reflections over the y-axis. And a is going to change how it shrinks or stretches. I'm always going to talk about, again, away from or towards the y-axis. If the a value is less than 1, we're going to say it stretches. less than 1, it's going to be stretching away from the y-axis. If it is greater than 1, then it's going to shrink the line towards the y-axis. All right, so when we talked about a factor for a horizontal stretch, it's going to be 1 over the absolute value of A. So the vertical stretch is just the absolute value of A. So you have to be mindful of the difference in the factor for horizontal and vertical stretches. And this means that for the first example, I am stretching by a factor of 2, right, because it's 1 over 1/2. And then I'm shrinking by a factor of 1/2, in this case 1 over 2. Okay, so please be careful, it's 1 over the absolute value of A for stretching and shrinking as a factor. Although the A value here is greater than 1, it's not a fraction, the factor becomes a fraction. And then vice versa, a fraction then becomes some value that's greater than 1 because it's 1 over that value. All right, so let's take some examples. I have f of a times x where a is between 0 and 1. All right, so now I am stretching away from the y-axis by 1 over a, which in this case is going to be 2. And so here's an example with y is equal to x plus 2. 1/2 of x, where I'm stretching away, becomes 1/2 x plus 2. And I should give you that information. So y is equal to 1/2 x plus 2 ends up being my equation here. So that slope becomes 1/2. My y-intercept is going to stay the same here because I'm not taking half of this value, the plus 2 value. All right, so let's move on. A is greater than 1. Similar example, f of 2x. And now I'm going to take here 2x, which I should write down again. Y is equal to x plus 2. And then f of 2x. And then it, in blue, becomes y is equal to 2x plus 2. All right, so let's take some more examples. Here's x plus 2. All right, so the 2 stays the same. I'm just multiplying the value of the term with x by 1/2. Slope is going to change. Y-intercept stays the same. All right, so let's take an example here again. F of x is equal to 2x plus 2. Right, and graph of function g is a horizontal stretch by a factor of 2, and then a horizontal shrink by a factor of 1/2. So we've got to be careful here, because I'm talking about factors now, which I have to translate to an a value. All right, so first I've got to translate to an a value. By a factor of 2, 2 is equal to 1 over a. A then is equal to 1/2. So g of x is equal to f of 1/2 of x. I know I'm moving quickly here. 2 times 1/2 of x plus 2 is equal to x plus 2. So 2 times 1/2 of x is equal to x plus 2. I'm going to graph the transformed function, same y-intercept. My slope is now half of the original function, 2x plus 2. I'm stretching by a factor of 2. I'm stretching away from the y-axis. Okay, now so second part, horizontal shrink by a factor of 1/2. So again, I got to translate this to an a value because the factor now is different in terms of its formula for horizontal stretches and shrinks. You have to make that translation with horizontal stretches and shrinks, but not with vertical stretches and shrinks. 1/2 is equal to 1 over a is equal to 2. G of x is equal to f of 2x, right, because a is equal to 2, even though my factor is 1/2. 2 times, now just the x value, 2x plus 2 becomes 4x plus 2. I'm going to write my original function, 2x plus 2, and 4x plus 2. Now I'm shrinking towards the y-axis by a factor of 1/2. All right, let's move on. Classwork 1.2.4. I'm going to give this to you. And then I'm going to pause. We're going to join up again. So please copy this down. You got a couple seconds or please pause because I have to end the video.